Okay, hello, welcome to the first video series in this class. So in these videos I go over the basic theory and most of the material and content you're supposed to learn. The videos are more or less dry, so I go over the theory and some of the examples, but I leave the fun parts for class. So to begin, this is a reminder for complex numbers. It is very important to refresh your memories about complex numbers. So that's what this video is about. Before going to talk about complex numbers, let's take a step back and remember what numbers are, including a complex number. And let's start with a real number. That's a number. Real number is, you can assume a line, an infinitely long line. If you take some reference value, call it 0, then real number is the position of a point along this line, real number A. So we associate a number to any point along this line, and there is infinitely many points. Let's also define something called unity or unit distance. Let's take this distance, call it unit. And we can look at a real number as a kind of a scaling of that unit distance. So number A, point A on the line, is essentially a scaling of this unit distance. Let me be consistent with my color. 1. If we multiply this by A, scale this distance proportionally, we can get to any real number. If it's on the other side, we get negative numbers. It scales the other way. So in some sense, you can think of real numbers as a form of transformation. It scales. It's an operator that if you multiply 1 by a number, it scales the distance. Now let's move up the complexity a little and enter complex number. As you can imagine, forget about all the I and J and everything you have seen so far. But quite simply, a real number was a point on a line. A complex number, let's call it Z, is a point on this two-dimensional space. So still we can continue having real numbers as a subset of this two-dimensional space. Still we have some origin, a unit distance, and some number A. Still everything holds in this, although we are looking at a 2D space, but it's still along this line, we can call real number A is a scaling of this unit distance. Now, how do we get out of this single dimensional line? Let's define a new operator. Our new operator, and that is rotation. So if we take any point, point A, and rotate it by 90 degrees, we can come off plane, offline, something that is no longer along this line. Let's call that operator J. So when we have a number, a point on this plane, Z equals J A, it means we are taking this point rotate it 90 degrees, we arrive at this point, call it JA. This is supposed to be a circular path. So we rotate by 90 degrees or 90 degrees or pi over 2. We arrive at this other point J. So you can see any point along this second axis is somehow another point B that is rotated, we arrive at JB. So now we can kind of give names. You see everything here is J times a real number. So I'm going to call this axis of real axis, and this other axis, let's call it imaginary, because we have real and something that is not real, imaginary. So you see J that we used to work with is in a sense a kind of rotation, and there is an inherent rotation built into complex numbers, built into J. Let's look at something funny. We can take any number and multiply it by J, it rotates it 90 degrees. So what happens if we take number, my first number is Z1 equals 1J, or simply J, this is J, and rotate it again by 90 degrees. That is, my point Z2 is, I want to rotate it, so I multiply by J, Z1, which is J times J, I can have a 1 here, and that is J squared, I'll drop the 1. So if I have this point and I rotate it another 90 degrees, I land at point -1. So I can write it here, J squared equals -1. And that is probably the more famous definition of J, that J is the square root of -1. To be honest, I don't know whether complex numbers started from here and it got the rotation came out of that, or originally Euler and all those people started with idea of rotation and could prove this. But in any case, you can see complex number, essentially J, is some kind of rotation. There is rotation built into J. So now we have covered all the points along the real axis, all the points along the imaginary axis. What we can do, and you have already seen it, let me divide up my screen. You have already seen it in vector algebra. Let's start here. This is my real axis, imaginary axis, and I have a point here, Z. What we can do, we can look at the components of this number along the two axes. We arrive at some real number A, and we arrive at some value JB. We can write Z as A plus JB. Essentially adding two numbers together, one real, one imaginary, we arrived at another imaginary number anywhere on this 2D plane. And needless to say, you can try to do anything with this number. For instance, you can multiply by J, which becomes JA minus, well, plus J squared B, which is JA minus B, and that is a 90-degree rotation of this point. I'm at the end of my board, so this distance should be equal to that distance. You see, if you multiply J by any number, you essentially rotate it 90 degrees. So now that we have seen what a real and an imaginary number is, just look at some of the properties of complex numbers. We just saw that J squared or equals J times J equals minus 1. This is the more or less famous definition of J. J inverse, remember we defined J as a rotation by 90 degrees, and I didn't mention it, but the direction is counterclockwise. The inverse of that operator, well, this is rotation by minus 90 degrees. So if you have number 1 and rotate it 90 degrees, you arrive at minus J. So J inverse multiplied by 1, this rotation equals minus J. So essentially, which means I can drop this, and J inverse is minus J, or 1 over J, which is this, equals minus J. You can very easily manipulate complex numbers. So if you have one complex number, A plus JB, you can add it to another complex number, C plus JD. You can add the components of it. So we will have A plus C plus J times B plus D. Same with multiplication, A plus JB times C plus JD equals, let me expand it. So I have AC, maybe I don't need this. AC plus JAB plus JBC plus J squared BD. I just saw this is -1, and I can collect or factor all the real parts and imaginary parts. I have AC plus or minus BD plus J times AD plus BC. You can do all sorts of manipulations with complex numbers. Now let's look at a very quick example. So I have the number. One number I have A plus JB. What is inverse of that? Or 1 over A plus JB. We usually don't like to, it doesn't show on the screen. I had written here A plus JB inverse. That's better. We don't like to work with, usually not a lot, having J on the bottom. We want to make it look nicer. So I can multiply it, JB, by something, maybe I should have covered it sooner. It's okay. I want to multiply by A minus JB. And see what happens. Here I will have on the top A minus JB. On the bottom I have A squared. I will have plus B squared. No, wait, what? Yeah, that's correct. B squared, because J times J is -1, that cancels with that. This is the real part. Plus, I have 1A times minus JB, 1 minus ABJ plus ABJ, they cancel. And this is the better representation or notation of the same complex number. Minus JB over B squared. We usually like to see complex numbers in this way rather than in that way. Okay. And a few more definitions. So first of all, the concept of norm, or the size of a number. If I have this point Z, this is BJ, this is A. Norm of Z is the length of that line, which is A squared plus B squared. I can also define angle of Z. Oh, before that, we usually use absolute value, or this is the norm sign of Z equals A squared plus B squared. This is the notation. I can also define angle of Z. We usually define it with this thing, phi, which is this angle, and it is from trigonometry, this is tan inverse of that over this, b over a. If we know the norm and the angle of a complex number, we can represent the same number, z, which is a plus jb. It's a different notation to write the same number. We can write it as norm and angle phi. This is two ways of writing the same number. If I want to spell it out, it's going to be square root of a squared plus b squared tan inverse of b over a. If you have such a notation, you have the norm and the angle. You can also construct back the two components. We have a equals norm of z, cosine of norm of z is this, time cosine of phi gives us a, and b is norm of z sine of phi. Something that I should have mentioned but I didn't up there is a very important naming convention. If you have a number z that is a plus jb, we can define another number, call it complex conjugate. We show it as z bar, which is a minus jb. So if I have my number here z, this is b, this is a, the complex conjugate number is going to be something on the other side with minus b, but the same real component. Okay, these are all basic definitions of complex numbers. Let me clean up the board and we can continue. So we were here that complex conjugate number, if we have z, a plus jb, z bar is a minus jb. So this is z, this is z bar. If you go back to our norm and angle notation, so if I have z, which is norm of z, angle phi, in this case z bar, the complex conjugate, has the same norm but negative angle. So angle is positive that way, so this is minus phi. We looked at the multiplications of numbers and they were a little cumbersome, but with this notation, phase and angle, or sorry, norm and angle. So if I have a number z that is equal to let me see what notation I use. Same norm of z, angle phi, and I have another number w with some norm and some angle theta. z times w, we can scale the norm of whatever the resulting number is. It's the multiplication of the norms. And the good thing about complex numbers, you remember rotation. So we have this number multiplied by that number, the angle rotates with that amount. Same for divisions. If I have z divided by w, it becomes very handy because the norms divide and the phase subtract. So this is a very handy way of working with multiplications and divisions of complex numbers. You can also extend it, for instance, if you want to raise a complex number to some power, which is z times z times z times n times that. You can use this way of calculation. You will end up at raising the norm to power n and rotating n times. And similarly for divisions, that if you have 1 over wn to the power n, which is w to the power minus n, this one is norm of w to the power minus n, norm angle rotating, this one had theta, or 1 over w to the power n minus n theta. So this norm and angle notation is extremely useful when we are dealing with multiplications of complex numbers, as we will see in the entire this course. That it's quite useful. All right, so now remember we defined J as rotation by 90 degrees. Now, if you are like me, itching to know what is rotation by some arbitrary angle theta. I was trying to find a very intuitive way to define it, but I couldn't. So let's go back to some basic math. So here is my number. So by that, I mean I have number 1. I want to multiply this number 1 by something x and cause it to rotate some arbitrary angle theta. The question is, what is that x? With that definition, we can try to work out a little trigonometry. Remember, this distance is 1. So we have arrived by transforming real number 1 and rotating by angle theta. We have arrived at this point z, which has a component a and b along the real and imaginary axis. So this becomes z, and my z is 1 cosine of theta. This is a. And plus j sine of theta, and that is b. Oh, maybe I can have a 1 here. So it's the same number. We are still trying to find that x. I'm just writing number z as just as a function of its components. Now it gets a little messy. Let's do Taylor expansion. Expansion, is that with S? Yes. Taylor expansion of this number. I need Taylor expansion of cosine of theta and sine of theta. So if you remember, maybe let's start with cosine. Respect the order. Cosine of theta. If you remember, that is 1 minus theta squared over 2 factorial plus theta to the power 4 over 4 factorial minus theta 6 factorial plus dot dot dot. Similarly, if we have sine of theta, it's theta minus theta 3 what is it? 3 factorial, is it? Yes. 3 factorial plus theta 5 over 5 factorial minus theta 7 factorial plus dot dot dot. Now let's use these two expansions to reconstruct that. So I have, so my z or x times 1 equals, I have 1 plus theta minus, it has a j, minus cosine doesn't have a j. So essentially I have to multiply this row by a j and add it to that one. So this minus theta squared over 2 factorial minus j theta 3 over 3 factorial. And the next one, 4 doesn't have a j, theta 4 over 4 factorial. You get the gist of it. Plus j theta 5 over 5 factorial and dot dot dot. Maybe it's a negative dot dot dot. So I'm going to now do a little trick. So I'm going to take out this minus sign, call it j squared. And this minus j, I take the minus, make it j squared, and multiply by this j, I have j cubed. I take this plus and make it j squared times j squared. Minus 1 times minus 1 gives me plus 1. So you see I can always create a j with the same power of theta and get the sign to work out. So essentially what I can write is 1 plus j theta plus j theta squared over 2 factorial plus j cube theta cube 3 factorial plus dot dot dot. All of them turn into pluses. What happened here? No. J theta cube. That's better. So I have 1 plus something is squared over 2 factorial, plus something is cube over 3 factorial, plus all of those. If you are like me, extremely smart, you immediately see that e to the, maybe call it little x, e to the x, if you do the Taylor expansion, gives me exactly the same thing. 1 plus x squared over 2 factorial, x cubed over 3 factorial, dot dot dot. Compare these two. Everything is the same. That means the x, the transformation that I'm looking for, is in fact e to the power j theta. This is a little weird to think about it. We are not really raising e to power j theta. To really get comfortable with it, you need to think of it as a function, and a function that is essentially a summation of all these power terms. And this is probably the most beautiful expression in the entire math. And if you do that, if you take that in mind, and let me use this space. So now what is rotation by pi, or 100 degrees, 180 degrees? You can easily write that e to the I pi. And what number is that? I have 1. I rotated 180 degrees. It arrived at -1. So this is, I believe, so this one is called Euler formula and this is a special case of that contains e, I, and pi, and -1, all the good numbers, and it relates all of them together. That is, in my opinion, the most beautiful equation in the entire math. It's so elegant, and it has a lot of concepts built into it that it summarizes a whole lot of math. Okay, good. So now we have this Euler formula that essentially, well, actually no, that's not Euler formula. What is Euler formula? That's not Euler formula. Euler formula is this part of it. Let me erase this. This is Euler formula. So remember, x was cosine of theta plus j sine of theta. That is e to the j theta. This is Euler formula. It's not as cute as that one, in my opinion. Okay, good. Good. What else? This one's dying. Okay. Let's see what else I have here. So a little bit of manipulation. I have e to the j theta. I just saw it. That is cosine of theta plus j sine of theta. I can easily write the opposite rotation. That's cosine of minus theta plus j sine of minus theta. Cosine of minus theta is same as cosine of theta. Sine of minus theta is minus sine of theta. Now I have two expressions involving sine and cosine. For instance, I can add this one and this one together. So e to the j theta plus e to the minus j theta. These signs cancel out. I will have 2 cosine of theta, or cosine of theta is e to the j theta plus e to the minus j theta divided by 2. This comes very useful when we are dealing with cosine and sine cosine in the context of complex numbers. Similarly, we can subtract the two, then the cosines would cancel. I'll have sine of theta would be e power j theta minus e to the minus j theta divided by 2j. And that is a very useful way of writing sine of theta as a complex number representation. All right. So the last thing I have is just an example. I put it right here. One example. Example for visualization. That imagine I have now a complex function. I call it f of t, which is e to some complex number. Instead of having e to j theta, I add another piece to it. So I can have sigma plus j theta. It's a complex number multiplied by t. I can, this is just an exponential, so I can write it as e to the sigma times e to the power j theta t. And this form is a very, no wait, I want to call it omega because it looks nice. J omega t. So this way is a very, 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 very common form that comes out in the entire course. And I think it's useful to have some form of visualization of this. Now let me do this, now do that. Okay, here I have the same number, z equals e to the sigma plus j omega times t. And on the bottom, I'm just visualizing how that number is changing. So what I'm plotting here is this back panel is a real and imaginary part of this number as time progresses along this time axis. So when sigma is 0, I have e to the t times omega j. And it is just a pure rotation. You see this point keeps rotating, rotating, rotating as the time progresses. Because I just have e to the some angle times j. As the angle increases, omega t increases, I have this spiral. I can adjust the frequency. Oh, what up? Don't do that. Don't do that. Okay. I can adjust the frequency of rotation, and you can see it rotates faster and faster in the same amount of time. Here 10 seconds. And the real and imaginary parts, which are sines and cosine of omega t, just oscillate back and forth. When I introduce the real variable theta, let's start with some negative number. What I have, let me get rid of this for a second. Going back to here, I have some e to the sigma multiplied by that e to the j omega. This is a rotation part. And I have some, this needs a time here. This e to the sigma t is an exponential function, either exponentially increasing or exponentially decreasing, coming to 0 as time goes on. Now coming back here, if sigma is negative, I have e to the some negative times time, and it's an exponential decay that is scaling both the real and imaginary parts. And this spiral eventually dies out. As I make it more negative, it dies faster and faster. And make it less negative, more time it takes for the oscillations to die down. Going back to 0, make it 0. Yeah, there is no dying down. This oscillation keeps going forever. And as I make it positive, now I'm multiplying the sines and cosines with a scaling factor that is essentially increasing with time. And as I make it more and more positive, you can see this spiral becomes bigger and bigger, and these oscillations exponentially grow in size. And this function just blows up over infinity. So that's all I have for now for complex numbers. In class, we will go over some examples. Let me make this bigger. We'll go over some examples. I stand here because it's nicer. And we will try to work with MATLAB to see many properties of complex numbers in practice.